Okay, the last thing to talk about with this wave example is what happens when you have a weak zone in the middle. So you can imagine this is something that could happen in reality. Up until now, we've been making models that were 100% elastic. In reality, you generally probably have some zones that are not elastic. And so we will see what happens in the case when the zones have the ability to fail. So this is the same wave example we've already seen. I've given this to you as a data file called yield.dat. Again, we're using the hexahedral zones in this case, just to make the waves a little bit nicer. Same elastic properties we've seen before, but now we're taking one zone in the middle of this column and we're giving it the group name weak. So between 25 and 26, there's a little weak piece. We're making this more Coulomb material instead of elastic material. And we're giving the same elastic properties, but now we're giving it a cohesion. And then the friction by default is 0. So this little piece has the potential to fail. As before, we're fixing the y and z grid point velocities. We're calling the wave function. We're applying the wave to the bottom, and we're watching it propagate up through the system. Recording some histories. One extra history here that we're recording is the stress, the maximum shear stress at a position right in the middle. So if we run this, actually, let's put this at 25.5 to make sure it's right in the middle of that zone. Okay, we haven't executed any steps yet because I want to show what happens as we go along. So here's this plot with the zones. Here's the weak zone in the middle, and it's showing the velocity vectors. They're all 0 because we haven't cycled yet. But let's start by cycling 100. So here comes the wave. Remember this trick of pressing the up arrow to give me another 100. Going, keep going. All right, here comes my wave. It's about to hit that weak zone. Now it gets interesting. Look what happens here. Here's the wave with the peak maximum velocity, a little bit more than 1. But when it goes past this weak zone, it can't support that amplitude. The amplitude of that wave is enough to cause shear failure in this weak zone. Because it turns perfectly plastic, it cannot support shear stresses higher than that maximum. And then it basically chops off the top of that wave. So we can just keep on cycling and see what happens. You can see how the flat part here, where the top of the wave has essentially been chopped off because it can't support that level of stress. And then the other interesting thing to see here is the reflection. So part of the wave passes through and gets chopped off, and part of the wave gets reflected and comes back down. Again, because of it's essentially a stiffness contrast. Even though we assign different stiffnesses, when it turns perfectly plastic, stiffness goes to more or less 0, and that causes a reflection. So we can just cycle another 1,000 or so. Oops, let's try that again. Have a look at the histories. So here's the input. Here's the middle. Notice that we actually get an increase in the amplitude here in the middle, just below that weak zone. Here we are at the top. Remember, normally the top would be double, would have an amplitude of 2, but because we chopped off the end of that waveform, we don't have the ability to see that doubling. And then here it is coming back down again, and it starts to get interesting because you're having reflections on top of reflections and so on. This is the velocity history. We can remember we took a history of that shear stress, maximum shear stress. So let's just make a new history plot here. Put on that maximum shear stress. Right, so you can see what happens here. The shear stress increases, and it can only get to that maximum 5 because that's essentially equal to the cohesion. It can't increase more than that. The zone turns plastic, wave comes back down, and then same thing happens on the way back up again. So, or potentially on the way down. So you can see the effect of this yielding zone. definitely does cause distortion of your waveform and other interesting effects. Okay, let's go back to the PowerPoint for a minute. Now we're going to talk about boundary conditions. Okay, so we've already seen what happens when you have a free surface. We get that doubling of the wave and it comes back down. We've seen what happens if you have a fixed surface. What happens then is you get zero displacement, obviously, but that the wave changes sign and comes back down, so you get a perfect reflection off of that fixed surface. What you often want to simulate is a quiet boundary, meaning that we don't want reflections off of the boundary, we just want the wave to pass through the boundary, as if there was an infinite amount of material on either side. So we can simulate that. There's a quiet boundary built into 3DEC, and again, it's easier just to show it. So let's go back to the original wave data file. So this we've seen many times already. Remember up here on line 13, if we fix the x velocity on the top, we get that fixed boundary, so the wave reflects off. Let's pretend instead that we want to have an absorbing boundary on the top. And the way to do that is you just say block, grid point, lie, viscous, range, position Z, 50. So the viscous is just another synonym for quiet. This is the quiet boundary. And in theory, what should happen now is the wave should propagate up through and then just disappear off through the top and not be reflected. So let's try and run this and see what happens. And we'll have a look at the histories. Oh, I'm plotting that shear stress. Let's go back to the velocities. So you can see the source halfway up at the top. Notice that it now does not double. It just passes by as if there's an infinite amount of material above us. Just to make sure that this is working correctly, let's cycle another 1,000. How about one more 1,000? Right, so we don't see any reflections coming back down, a little tiny bit here, but a negligible amount of reflection, indicating that our viscous boundary is working and those waves are propagating off and not reflecting. So that's great. If you've got a model where, let's pretend you have a tunnel being subjected to an explosion, you could put quiet boundaries on the sides, and then that energy from the explosion will just disappear off through the sides of the model. It gets more complicated when you apply the wave to the edge of the model rather than the middle, because what we don't want to happen usually is to have a reflection off of that bottom. So for example, let's just go back to our data file here and let's comment out that viscous boundary. And let's make this like 3,500 steps. So now we are applying the velocity to the bottom of this model. So we're shaking the bottom in the x direction. It makes that sine wave and then it stops. It holds the velocity at 0. We already know if we hold the velocity at 0, we're going to get a reflection. All right, and we can just prove that to ourselves quickly by running this again. So here's the source halfway up at the top, coming back down. Now what happens is it actually bounces off the bottom, which is fixed, and comes back up again. That we do not want. If we're actually trying to simulate an earthquake on the bottom of a model, we would want anything that's coming down to pass through the bottom and continue on and not reflect off of the bottom. How do we do that? If we fix the velocity on the bottom, we're going to get a reflection. So we can't fix the velocity on the bottom. If we set a viscous boundary on the bottom, then we can't specify the velocity. Those two things cannot exist at the same time. So what we need to do is instead give a stress boundary condition. the stress boundary condition and the viscous boundary condition can exist at the same location, and everything will work. So now the trick is to figure out what stress to apply to get the velocity that we want. Okay, and there's an equation for that, so it's actually relatively easy. So if we just quickly go back to the PowerPoint, here's what I was saying. We can't apply a velocity at a quiet boundary because the quiet boundary would be nullified by the imposed velocity condition. Therefore, we apply a stress condition that is equivalent to the velocity. And the trick here, again, is to figure out what stress to apply to reach the same amount of velocity. And it turns out you can figure it out with an equation. And the equation is this. If we're doing shear waves, the shear stress that needs to be applied is -2 times the shear wave velocity times the density times the velocity that we actually want. Okay. There's a factor of 2 because the input energy divides into a downward and upward propagating wave. So that's it. We just need this equation. If we go back to our example, I've actually given this to you in a comment. So let's get rid of this applying as a velocity and uncomment lines 24 and 25. So here we're setting a viscous boundary on the bottom and applying a stress to the bottom. We want an XZ shear stress. And then this equation, remember, is -2 times the shear wave velocity, which we know is 1,000, times the density, which we know is 1,000, times the velocity that we want, which we know is 1. That was the velocity. It can use the same fish function to vary the stress. So remember, the fish function just returns a value between 0 and 1, multiplied by whatever we specify. So it's still returning a value of 0 and 1. It's just that now it's multiplying that by -2e6 instead of 1. In theory, we should get the correct response, and we should not see a reflection off the bottom. So let's run that. Have a look at the histories. Okay, source wave, halfway up, bouncing off the top, coming back down, passing through the bottom. Again, this is like the viscous boundary we showed on the top. It passes right through. It doesn't double, it doesn't reflect. And then we see nothing after that. You can run a few more steps if you want to convince yourselves that that worked. Right, so it bounced off the top, passed through the bottom, and everything worked. And you can see the velocity amplitude here is 1, which is what we were trying to achieve with that equation. Okay. Couple more slides. All right, like I said, you can have an internal source and you can put quiet boundaries on the sides and it works great. This is just a nice little movie showing pulse being applied to a tunnel. And what we've got here is a free surface on the top, so we're getting that doubling effect. But we have viscous boundaries on the sides and the bottom so that the waves basically disappear off into space. This example is included with the material that you will have downloaded. I won't go through it in this course, but you can go through it on your own time if you want. Let's watch it one more time here. Here's the source, doubling at the top and passing through the sides. One thing to be aware of, if you're using these viscous boundaries, you want to get to the initial stress state first, and then apply the viscous boundaries, and then everything will be balanced. Everything will be okay. If you put the viscous boundaries on and then try to get to the initial stress state, some weird things might happen. Because they're essentially stress boundary conditions, so you can see rotation of the whole model and things like that. But if you're at the initial state and everything's balanced, you can just throw on these viscous boundary conditions and it will be okay. Note that the quiet boundary is only a perfect absorber when the waves are perpendicular to the boundary. So in the simple example we showed, the wave is perpendicular to the boundary, it just bounces off of it and or does not bounce off it in this case, and they get more or less perfectly absorbed. If the wave is coming in at an angle, the viscous boundary condition is not perfect. You might see a small amount of reflection. So bullet point 3 here, even if you're using quiet boundary conditions, you should try to put the boundaries fairly far away from the area of interest, just in case you get some little reflections due to the imperfection of these viscous boundary conditions. Okay, next thing to worry about when it comes to boundary conditions. Let's pretend you're simulating an actual earthquake. And so for our one-dimensional model, it was relatively easy. We just send it up through the model and everything works. In reality, you have a three-dimensional model. And this gets more complicated because of what you need to do at the sides of the model. So we want this to propagate upward like a plane wave. Imagine that the earthquake is, way down below here somewhere. By the time it gets to your model, it's a giant wave, and we want it to propagate up through the model as a plane wave. But we also don't want things to, for example, reflect off the tunnel and then reflect off the sides. We definitely don't want to have reflections off of these sides because they're not real boundaries. So you think, okay, I'll just put quiet boundaries on the sides. That's fine. But what that does is it absorbs part of the energy of the incoming earthquake. So we're shaking, imagine we're shaking the bottom here, left and right. Some of that left and right motion gets absorbed by these quiet boundaries on the way up. So you get a distorted wave coming up through the system. It's not a perfect plane wave anymore, especially close to these boundaries, because the quiet boundaries are absorbing some of your energy and it's a mess. So what do we do? There's something built into 3DEC called free field boundaries. And basically, they were just designed to solve this particular problem. And without going into too much detail, what it essentially does is adds extra blocks to the sides of the model with these dash pods, and it behaves as if the wave is free to move upwards, and the left and right vibration is unaffected by these boundaries, but at the same time, you don't get reflection off of these boundaries. So it's basically a way to solve this problem of a giant earthquake coming in through the bottom, and you don't want reflections off of the sides. So here's the same model that I just showed you with the quiet boundaries. Now we're using these free field boundaries, and using these boundaries is super easy. It's just one command: block dynamic free field apply. By default, it assumes that you want the boundaries on the sides. You want the top to be a free surface, and you want the bottom to be your source. So basically, it's assuming that Z is vertical. It will automatically put these free field boundaries on the left, the right, and the front, and the back. And if that's your situation, then you're all set. All you need is this command, and it works great. You can see how this wave is not being distorted at the sides, and it's propagating upwards like a plane wave, which is what you want. If you have a different kind of geometry, there are other keywords in here where you can specify free field on different sides and things like that. Most of the time, you don't need to do that. Okay, that's everything about boundaries. The next thing is about damping. So everything we've done up until now has had no damping. So those waves, depending on your boundary conditions, will bounce up and down through this column forever. Obviously, that is not what happens in reality. You possibly want some damping to take energy out of that system so the waves don't bounce up and down forever. However, there are mechanisms that remove energy from the system that are not damping. So, for example, if you have joints that are slipping, you lose some energy here due to friction and heating and so on. If you have quiet boundaries, obviously you lose energy through the boundaries. We've seen that already. If you have plastic flow, you lose energy in that situation. Our example was not very convincing because there was only one zone of plastic flow there, but you can imagine if you had a larger volume of plasticity, you're definitely losing some energy in the system. So it is possible to run a model with no damping and still see fairly realistic results, depending on how many joints are failing and how many zones are failing, what your boundaries are. However, most of the time, people will put a small amount of damping in the system to prevent unrealistic wave propagation for a long time. The problem is that the default damping that 3DEC uses, so when you're not using config dynamic, there is a large amount of damping in the system because it assumes you just want to get to a steady state relatively quickly. And that's fine because you do not care about the waves that are propagating through the system. You only care about getting to that steady state solution. If you do care about the waves propagating through the system, that type of damping is not good because it's frequency dependent. So it preferentially damps out some frequencies over other frequencies, and it will distort your waveform as it propagates through. So what we need is some sort of frequency independent damping. And this is what we need when we're doing dynamic analysis. And so traditionally, the type of damping that has been used is called Rayleigh damping. And what this is, without getting into too much detail, is two different components. There's a mass component, which acts like a dashpot, and there's a stiffness component, which acts slightly differently. And it's easier to show on this graph. So here we're showing a graph of frequency of some wave. And here we're showing on the y-axis the ratio of damping to critical. So essentially the amount of damping that occurs versus the frequency. And you've got two different lines here. So there's this mass proportional part, which is this dotted line. And you can see that it preferentially damps out the low frequencies. You have this stiffness proportional part, which is this straight line, and it preferentially damps out the high frequencies. So either one of these by themselves is not that great. But if you put them together, you end up with a flat portion here. So this curve here is showing the addition of the stiffness part and the mass part. And what you see is between about roughly 7 and 17 hertz, you get a relatively flat response here so that all of these frequencies are damped more or less the same. And so this is the way that Rayleigh damping works. You don't necessarily have to understand all the math. You just need to know that if you're using it, you need to specify some frequency, because what it will do is it will try to work out the components here so that you have a flat response close to that frequency. So this can potentially be a challenge. I mean, in our case, it's easy. We're putting a wave through with 40 hertz. It might not always be that easy to figure out what your frequency is. I'll show that on the next couple of slides. You also need to give some critical damping ratio. So if your number was 1, that means it's 100% damped and nothing happens. If your number is 0, that means there's no damping and it just propagates around forever. Usually you're specifying some number like 0.02 to 0.05 as the amount of critical damping. So this sounds great. The two problems with Rayleigh damping are, number one, you need to figure out what to put in for the frequency. And it's, again, not always obvious how to do that. Number two, and this is potentially more important, is it reduces your time step. For mathematical reasons that I don't want to go into, the stiffness proportional part of the Rayleigh damping causes your time step to be reduced. And this reduction can be quite significant depending on the amount of damping that you're putting in your system. We can show that. So let's go to our example here. So here's our example. We'll just leave it the way it is, but we're going to add some damping now. Remember, when I say model config dynamic at the top, it automatically sets the damping to 0, and it automatically turns off the mass density scaling. So I don't have to do anything to get 0 damping. But if I want some damping, I need to specify. So I need to say something like block, mechanical, damping. I'm not 100% sure of the keyword, so I hit Control Space here just to double check. Rayleigh, right? So I choose Rayleigh. And then it's looking for two numbers here, F1 and F2. I know one of those numbers is the frequency, and I know one of those numbers is the percentage of mass sorry, the percentage of critical damping that I want. I can't remember which one is which, so I can right click on here and say, go to the actual help. Close this. Now I can look at the help here. So here's the command, Rayleigh F1, F2, and it tells me here, F1 is the fraction of critical damping, and F2 is the center frequency. So the first number, let's put in, I don't know, 0.03. And for the frequency, we can just say 40. We know that we have a wave of 40, so that's easy. All right, let's see what happens here. We can put this back to 2500. So here it goes. Let's have a look at our histories. Wow, okay. The first thing we notice is that we haven't progressed very far in the simulation. We've only got half of the input wave. And this is a perfect demonstration of the problem with Rayleigh damping, is that it kills your time step. So if you look here in the console, the time step is 3.9888 E minus 6. When we ran this last time, if we scroll up, the time step was 4.4 E minus 5. The time step is almost 10 times smaller now than it was before. So in order to finish my simulation, I need to run a lot more cycles. So I'm going to say model cycle, I don't know, 10,000. Let's do another 10,000. Okay, so it takes longer, but you can see that it's actually working. So here's the input wave with an amplitude of 1. Here it is halfway up with an amplitude of roughly 0.9. Here's the reflection off the top. Remember, with no damping, it has an amplitude of 2. Now we're at about 1.5. Here it is coming back down again. The amplitude's at about 0.6. So you can see the Rayleigh damping is taking energy out of the system. You can also see that it's not distorting our waveform. We're still getting relatively nice sine wave here, which is what we want. Just for fun, we can use the damping that comes with, the default damping when you're not running dynamic, just to show you why you shouldn't use it. If I go back to here, instead of block mechanical damping Rayleigh, I can say block mechanical damping local. And then again, with the local damping, I can give a percentage of critical. For this to work, I need to give something higher than 0.03. You won't see anything happening with 0.03. Let's try 0.1. So this is nice because it doesn't kill your time step. So you may be tempted to actually use this. But if we look at the histories, you can see what's happening here. So it's decreasing the amplitude a little bit, but it's also messing up my waveform. You can see here this weird spikiness to the wave, and you can see this dispersion here at the bottom. If you really want this to get ugly, we could bump up the amount of damping here just to show you. So again, you can see the decrease in the amplitude, but wow, it's really starting to look like a mess. So if you're concerned about the integrity of your waveform, you probably don't want to do this. And use Rayleigh damping instead. Now, the question is, okay, Rayleigh damping is great, but it's killing my time step and it's taking me forever to run my model. There's another type of damping that's relatively new in 3DEC called Maxwell damping. So what this is, it's a similar sort of idea in that you have multiple components that damp out different frequencies, and you stick these multiple components together to get a flat response. So you can see the graph here on the right. I've got this one component, which is the black dotted line, one component, which is the green dotted line, one component, which is the blue dotted line. And I put them all together, and I get a fairly flat damping response over a range of frequencies. So this overcomes the Rayleigh damping drawbacks. It does not reduce your time step, which is the main reason for using the Maxwell damping. And I didn't talk about it, but it also does not overdamp the high frequencies, which you sometimes see with the Rayleigh damping. It's a little bit more challenging to use because you need to worry about these multiple components. and there's a little bit more user knowledge required to use this. I am not going to go into details about Maxwell damping in this presentation. I have included another whole presentation just about Maxwell damping. It's a PDF. You can open it, you can look at it. There are also examples in the manual of using Maxwell damping in 3DEC. If you are interested in this, I encourage you to go and have a look at it. Okay, last topic, partial mass density scaling. As discussed many times already, the time step in 3DEC depends on the stiffness of the zones, the size of the zones, and the density of the zones. The static analysis, when we don't really care about the integrity of our waveform, we do this trick where we find the smallest zones and the stiffest zones, and we increase their mass so that they don't kill the time step. And we do it in such a way that it doesn't change their vertical displacement due to gravity. It's sort of a behind the scenes thing that just increases the mass that is used to calculate the time step. And so this is called mass density scaling. And it works great if you don't necessarily care about the the integrity of your waveform and you're just trying to get to a steady state solution. When you give the command model configure dynamic, it automatically turns this off. So there is no mass density scaling. And what that means is if you have very small zones or very stiff zones, they will kill your time step. And that is a problem. And this kind of thing happens all the time in 3DEC because you are often cutting things with that block cut joint set command or block cut discrete factor network. And you can potentially end up with very thin little slivers. And again, the time step depends on the size of the zones, or in fact, the minimum dimension of the zones. So ending up with these tiny slivers will really kill your time step. And often you don't really care about the accuracy of the waves around these tiny zones. You could imagine a case where you've done a bunch of these cuts and you've got some tiny, tiny zones off in the corner somewhere, and they're killing your time step, and you don't really care about the fact that, when your wave passes by them, it might get messed up because it's off in the corner somewhere. So what we have is this concept of partial mass density scaling. And so what you can do is just find the smallest, stiffest zones and scale them without necessarily scaling all of the zones in the model or all of the grid points in the model. Not sure why my face is appearing here, but so the way it works is you you define the time step that you want. Okay. 3DEC will automatically adjust the mass of the grid points if they would cause the time step to be smaller than that. Okay, so it does not adjust the mass of all the grid points in the model. It only adjusts the mass of the smallest grid points or the stiffest grid points. It outputs to the screen how many grid points have been affected and how much mass has been added to the system. So it's kind of up to you as the user to figure out whether or not that is acceptable. Obviously, if you're adding a whole lot of mass to the system, it's going to cause distortion of your waveforms and other problems. If you're adding only a tiny bit of mass to the system, maybe you can increase your time step a little bit more and make your model run faster. What you will find out, you can try a bunch of different time steps and see how much mass is added. And if you plot it on a graph, you'll see something like this. So generally, you can increase the time step, increase the time step, increase the time step. It has not much effect because it's just picking off these little tiny, tiny zones until you get to a point where it starts picking off a lot of zones and you see a rapid increase in the mass added. So what you want to do is find the sweet spot here where you're increasing your time step, but you're not adding a lot of mass to the system. And there's a guess. You can sort of make a guess here at, a dt of something on the order of 1/10 of the average zone size divided by the p-wave velocity. And as always, it'll be easier to show this in an example. So let's just go back to 3DEC. We'll open a different example. So I'm going to say open. Go up one level, and I've given you this project called density scaling. I can open it, mscale.project. Okay, so here's a relatively simple model. I'm using configure dynamic, so it's turning off damping, it's turning off density scaling. I'm turning off large strain. I'm making a 2 meter by 2 meter by 2 meter brick. I could have made this simpler, just like this. I'm making 4 cuts. And the reason I'm doing that is I'm intentionally trying to make a very skinny little block so that it will mess up my time step. I'm generating zones. I'm giving it elastic properties. I'm specifying contact properties here. Again, I'm just applying a wave to the bottom. In this case, it's a very simple little function that just applies a sine wave with a frequency of 100. I'm specifying, sorry, this line 37 here is where I'm applying the wave with a velocity of 0.1 using that sine function to the bottom. On the top, I'm using a viscous boundary. I could have made this simpler. I don't need to specify 3 directions of viscous. I can just say viscous. So the bottom is the input wave. The top is absorbing boundary. The sides are all fixed. So it's essentially a plane wave moving up through the system here. I'm recording velocity at 2 points, the bottom and the top, and the dynamic time, and then I'm going to run it. Here's where I say model solve. You can give a time. Up until now, we've been using a number of cycles. I can say model solve dynamic time and give a time instead. This is in seconds. So I run this. You can see my time step is 1.2 e minus 6. It takes 8,000 steps, a little bit more than 8,000 steps to reach my dynamic time of 0.01. I can look at my history. So the source wave is the blue one, and the wave at the top is the green one. You can see that the wave propagates nicely through the system, does not get distorted, which is great. Again, remember, there's no damping here. But let's pretend this is a real model, and my time step of 1 e minus 6 is quite small. And I think that this model is going to take a really long time to run. I want to change that. If I look at my model, if I go to the blocks plot, you can see what's happened here. I've made the cuts in such a way that I've ended up with a tiny little skinny piece of a block here. And again, it's this tiny dimension here that's killing my time step. And pretend it was a model with, I don't know, a tunnel in the middle where I was interested in it. This tiny little guy over here on the side, I don't really care about what happens over here. So I can increase the mass of these grid points, which will increase my time step and will not have a dramatic effect on the behavior of the model. And so the way to do that, so I'm going to restore that initial state that I've already created. So my time step before was roughly 1 e minus 6. Let's make it 1 e minus 5. So let's see what happens if I make a 10 times bigger time step using this command, block mechanical mass scale. And again, this will not scale all of the grid points. It will only scale the smallest grid points, or the grid points attached to the smallest zones. Same command, model solve dynamic time 0.01. I'm changing the history interval here because now the time step is 10 times bigger. It's going to require 10 times fewer steps. By default, it only records the history every 10 steps. And so I won't necessarily get a very nice picture of my wave if I'm only recording it every 10 steps. So I can change it to be an interval of 1. So anyway, I can run this. What you will see, as soon as I start cycling, it dumps this information out to the screen here. Let's make it a little bit bigger so you can see it. Partial mass density scaling. Number of scaled grid point mass is 70. A bunch of other information. The important stuff is down here at the bottom. So total added mass in the model, 3.5580 minus 3. Total real mass in the model, 1.92 e minus 2. Added mass divided by real mass, 0.18. So I'm adding, roughly 18% to the mass of this system. Again, it's kind of up to the user to decide whether that's okay. What you would do, or at least what I would do, is I would go and have a look at the histories and see if everything looks okay. Let's make this. Right, so there's my input wave. There's my recorded wave. You can see that it's almost perfect. It's slightly wiggly. If we compare that to the case where there was no mass density scaling, slightly smoother, but really the difference here is negligible. With the added benefit of a 10 times bigger time step, it only required 1,000 steps to get to this point instead of 8,300 that it required last time. So that looks great. But now you might get greedy and say, oh, okay, I increased my time step 10 times. Let's increase it another, I don't know, let's make it 5e minus 5 instead of 1e minus 5. And run that. Now it only requires 200 steps. Fantastic. But if I look at my histories, this is a disaster. Something very strange is happening to my wave. If I look at the information printed to the screen, now the number of scaled grid point masses is 282. Remember, it was 70 before. Total added mass was 0.2. The total real mass is only 0.02, so it actually is adding a whole lot of mass to the system. It's, you know, 1,000% extra mass added to the system. So it's more or less scaling all of the grid points. We can actually see how many grid points are in it. If you give the command model, log list max, gives you some information that's useful. Number of blocks 14, number of vertices 282. And so it's scaled 282 grid points. It's scaling every single grid point in the model, which is definitely not what you want. And that's why you're seeing this screwed up waveform. So this partial mass density scaling is totally useful in 3DEC when you end up with really tiny blocks. You just have to be careful when you use it to not get too greedy and make sure you look at the diagnostics when you use it to see how much mass is being added. And it's always advisable to also look at the, and maybe do one experiment where you're looking at the waveforms to see that it's not being distorted too much. Okay, that is the end of the dynamics section. Thank you for joining.